So yeah, it's a pleasure to introduce and announce a new utility package that we use in our modeling called PiecewiseAffineApprox, and it's to generate piecewise affine approximations. As you can, it was registered last week, so if you want to check it out, I will just give a brief introduction to our team and the motivation for doing this kind of stuff, and then I'll try a live demo. We had some issues with that earlier, but I think it's going to work, and then show how we can use it in some energy applications. And I forgot to mention that this is joint work with my colleagues at SINTEF, Truls Flatberg and Thiago Silva. So we, as Truls told you about yesterday, we are at SINTEF. Our group is a small part of a large research institute, and we are located in the the sustainable energy technology department. And we do mostly mixed integer linear programming optimization, modeling, mostly in a variety of different sectors. And as you heard yesterday, we are moving towards doing more open stuff, and in particular, we are doing more modeling in JUMP and using Julia, and we have started to share some of our packages with the public. And these are some of the packages that have been presented before. And the motivation for doing this package is that we often find that we have some non-linearities that we want to include in our models, but we want to do it in terms of linearizing everything, basically. And when we work with our colleagues in the more technical parts of SINTEF, or maybe with customers, they will often use more detailed dynamical models. Usually they don't use Julia for this yet, so we can't just integrate everything, and we will usually just get a set of points to describe some of these non-linearities. And then we have to figure out a way to include it in our model using some kind of linearization. And we found that it's nice to have a library to do this, so it's much easier than to update our approximations when we get updated data. Maybe they did some new experiments, or they updated their model or something. And we hope that this can be useful for others as well. And also we hope that by sharing it, we can get some feedback from others trying it out, and maybe improve the robustness and quality. So the general idea is that we will generate some piecewise affine approximation from a set of point estimates. We also have some convenience functions. For example, if you actually have the function expression, then you can do the sampling automatically to use the same framework. For now, we have concentrated on convex or concave functions because the main motivation is to achieve efficient models that we will solve in the end. And we have implemented so far 3 main methods, I would say. So it's the first method that we implemented was to generate a mixed integer linear program to find the best approximation. And this is based on the model by Torriello and Vielma. And that works very well, and it's kind of cool to optimize the formulation of the optimization problem that you're going to solve. But it also has some issues in some cases, and it's based on this big M formulation, and it turns out that finding a good big M is non-trivial in some cases. So we have also had some good experience with some of the other methods that are more heuristic versions. So there's a clustering-based method based on the work of Magnani and Boyd. And most recently, we have added a method that progressively builds the approximation by adding planes. And then in the first two methods, you specify more or less how many planes you would like to use for the approximation. And in the progressive, you have you can set a target for the accuracy of the approximation instead. This is to illustrate how you can use it. So you will just you can just use the package. It's now registered in general, and we first here just define some test data and we'll just use a simple quadratic function to demonstrate how it works. And an interesting part happens down here. So this is where we actually generate the approximation by calling this approx function, and then we have defined different types for the different methods. So in this case, we are using the MILP approximation, and it's for a convex function. And this way, we use the multiple dispatch to switch the direction if it's a concave function, and everything just works out fine. And you have to pass the optimizer and you can set some options for the different methods, and so you can define which metric you want to optimize. So it could be the L1, L2, or the maximum that you want to minimize. You can supply the number of planes that you would like to have in your approximation, and we have some options also how you would like how your approximation should be, if it should be just the best fit, or if it should be outer or inner approximation. And then you get back this object that encodes the result of this, and that includes all of the different planes that were calculated by the method that you chose, basically. So just to give you an illustration, and this is where we will see if the risk pays off in doing the live demo now, but hopefully you can now change the number of planes that we supplied, and it will update the approximation. So you can set the number of planes, and you will get different solutions depending on how many you solve. The red points here that are the points that we're trying to approximate, and if you now change the what we call strictness to get the outer approximation, then it will re-optimize, and you will get an approximation where all of the points are within the approximation. So we think this is we hope this can be interesting and useful for others as well. We have a 3D example. So this was what was causing the issue with my presentation, because it turned out that solving this small example on this machine just wouldn't converge. So, but that's kind of illustrating also a bit why we want to do this, because sometimes it can take quite some time to do these approximations. But if you do them offline, then you can store it and use it in your model when you solve it repeatedly, and then everything will be performant. And I will just briefly mention that we use this in some of our energy applications. So some of the data that we typically get will be efficiency data for the different processes, and I will show you an example on a fuel cell. And If you would like to hear more about this, I will give a bit more context about this on my ISMP talk on Tuesday. So you're more than welcome to come there as well, or talk to me afterwards. But we will typically get an efficiency curve that can look something like this. And as you can see, the fuel cell has a better efficiency when it's running on a lower load, and it reduces as you increase the load. And this is something that we would like to be able to include in our models. And we can use this package to do that quite easily. And we will then first just transform it from this efficiency to the relationship between the input and the output. So how much output you get at the different set points for the fuel cell. And then we can. So this is just to transform the data to get what you see down here. And then we compute the approximation like this, and then we get a nice piecewise affine approximation that you can include in the model. And we actually have some utility functions also to directly add the constraints to the model. So this illustrates also how nice it is that you can do everything in Julia and just combine different packages. So yeah, so that's more or less it. We still have some ideas on how to improve the interface. We would like to improve the robustness a bit, maybe find a better way to compute the big M so we can more often use the MILP method. And we are also open to implement or accept PRs with new methods, maybe. So please have a look, give it a try, and let us know what you think.